Let's start with our next speaker. He's Tien-Cuong Dinh, originally from Vietnam, and he moved to Odessa as undergraduate, and then to Paris, where he stayed for quite some time. He, in fact, became professor at University of Orsay, and right now he's a professor at the National University of Singapore. The title of his talk will be Pluripotential Theory and Complex Dynamics in Higher Dimensions. So please.
Thank you very much. I'm very happy to be here in this so wonderful country. I'm very happy to be speaker at this ICM. I'm going to discuss, to report today some recent developments of the pluripotential theory, and we'll give some application in complex dynamics in higher dimension. So let me first introduce this two theory. So let X be a compact Kähler manifold of dimension K. Take, for example, the projective space Pk or any other compactification of Ck. We consider a holomorphic map or a meromorphic map from X to X. So by meromorphic, we accept here some singularities for F. And we can even consider correspondences, means that multi-valued map. And then we can define the iterate of order n of F by composing F with itself in this way. And the main problem in dynamics is to study the sequence F, F2, the sequence of iterate when n go to infinity, and also the sequence of the inverse of this Fn. So this problem includes the study of the distribution of the orbit of points or varieties. So if you take a point or variety V and consider the orbit or the backward orbit, and we want to study the distribution of this sequence in the space. Another problem is to counting and the number of periodic points. That means that we consider this equation Fn x equal to x and study the distribution of the solution on the space. Also, we have to study the dynamical invariants, including the degrees, the entropies, invariant measure, currents, or invariant sets like a Fatou set or Julia set. And one more problem is is a problem of classification of the dynamical system, including the construction of new example. It's not easy to construct a new example. It's also difficult to prove that the example is new. So in dimension 1, the theory was founded by two French mathematicians in about 100 years ago, Pierre Fatou and Gaston Julia. The theory is now very developed, and the main techniques that people use in this theory are quasi-conformal maps, and also the help of computer to see the Julia set, for example. And many people contributed to this theory, so I have here a very short list of those people. And the most famous example is the quadratic polynomial, z squared plus c. So in this picture, you have the Mandelbrot set, which is the moduli space for this family of dynamical system. So the system depends on the position of C with respect to this Mandelbrot set. So when you move from one component to another component, the dynamical system can change a lot. So let me give you a very simple example where C is equal to 0. This is almost the unique example where you can compute everything easily. So Fz equal to z squared and Fn z equal to z to 2 to n. So you see that if A absolute is smaller than 1, means that we are inside the unit disk, then the orbit of F go to 0. And in this yellow set, the dynamics is somehow stable. Because if you change a little bit the value of A, then A is almost always smaller than 1, and the orbit still go to 0. And you have the same picture if A absolute is larger than 1, then the orbit of A go to infinity. And the picture is similar to this one. So the yellow set here is the Fatou set for this dynamical system. And the unit circle S1 is the Julia set. And the dynamics on the Julia set is unstable. So if you take a point on the unit circle, then if you change a little bit the value of A, so it can be smaller than 1, and then the orbit go to 0, and if it's larger than 1, then the orbit go to infinity. So the Julia set is a set where the dynamic is somehow unstable. Okay, so let me give you some more picture. So in this, in the first picture, if you take a generic point e to I theta, then the orbit of this point is going to equidistributed on the unit circle. So this exactly the law of large number is in probability theory. So we can say more about this. For example, we can have central limit theorem or last deviation theorem, but it's a little bit technical to stay here. So I pass to the second picture. In the second picture, we have the set of periodic points of period n. So that means that we consider the equation z to 2 to n equal to z. So 0 is a solution, infinity is a solution, but the other solutions are equidistributed on the unit circle, like that. Okay, so one more picture. So if you consider the pullback of A by Fn, it means that this set F minus n of A, which is the set of solution of this equation, and you see that except for A equal to 0 or infinity, the solutions are equidistributed near the Julia set, like that. This is an easy exercise. Okay, so this is the case of a very particular example, but all the properties that I stated before basically hold in the general case. So here you have the picture for Julia set of z squared plus c for c equal to this number. So we have the same statement, except that the Julia set now is much more complicated. So this is the boundary of this set, but basically you have the same properties. Okay, so now I pass to the higher dimension. The theory is more recent and is a very fast growing research domain after the work by Bedford, Lubick, Smiley, and Fornais-Sibony. So the main tool that we use here in this theory is the pluripotential theory, and more precisely, the positive closed currents and their intersection. So for example, you can consider a map, polynomial map from Ck to Ck, and then you can compactify Ck to get a rational map from Pk to Pk. So you may have some singularity at infinity. And we have many other examples by Bedford, Kim, Major, Macmillan, and more recently by Macmillan, Ogiso, and his collaborators. So I give here some difference between the case of dimension 1 and the case of higher dimension. So first, in dimension 1, the map is conformal. outside the critical set, and roughly we have only one direction, and roughly the system is expanding. But this is not true in higher dimension. You might have some expanding direction, and you might have some contracting direction. And the system here is holomorphic in dimension 1, but it's not always continuous in general, because you might have some singularity. So for example, you see here, in this example, in C2, you consider the function z1 over z2. So when z goes to 0, the limit depends on the direction that you go to 0. So you don't have a value of this function at the point 0. This is a new problem in higher dimension, and the orbit of the singularities might be complicated. And this is a big problem for the theory. Also, the action of the map on the cohomology is very simple in dimension 1, but in higher dimension, this action can be unstable in some sense. And finally, computer is very useful in dimension 1, but not yet in the higher dimension. Okay, so now let me introduce the main tool in the theory of dynamical system in higher dimension. So this is the pluripotential theory, or Lelong-Oka theory, which was founded in around 1950 by Lelong and Oka, and there are many important contributions by many people, including Benson, Demay, Hormander, Sibony, Siu, Sukoda. This is a very powerful tools in complex analysis, complex geometry, dynamics, and foliation theory. So I'm not going to give you the formal definition of positive cross currents, but the idea is the following. So you can see that the probability measure are generalized points. So if you have a point, then you have a Dirac mass, which is a probability measure. So we can see that a probability measure is a generalized point. So now, in higher dimension, positive cross currents are generalized subvarieties. So this is similar to the case of dimension 0, except that here the dimension can be positive. Or you can consider cycle. Cycle means that you take a finite combination of varieties or points. But here we are talking about higher dimensions, so then you can consider the intersection of those objects. So intersection theory is a very important part of the Lelong-Oka theory. Okay, so let me be more precise about this. So a positive measure is exactly a positive cross current of maximal by degree, kk. So consider an zero cycle of degree 1, so something like that. So here, lambda I is a real positive number, and AI is a point in X. And I assume that the sum of lambda I is equal to 1, means that the degree of this cycle is equal to 1. Then we can associate to this cycle a probability measure, which is the summation of lambda I, the Dirac mass at AI. So that means that I can embed this space into the space of probability measures on X. But now, this space is compact for the weak topology, so we can see that this is one way to compactify the space of effective zero cycles of degree 1. Okay? Then, probability measure can be seen as an element of the D1 space of the space of continuous function. So star here stands for the D1 of this space. So more precisely, if you have a probability measure, If you have a probability measure and a test function, then the value of mu at phi is simply the integral of phi with respect to this measure d mu. So we have the smooth case. In this setting are simply positive differential KK forms. So you can think about volume form. If the volume form has integral 1, then you have a probability measure. It's like a Lebesgue measure. And it's easy to show that smooth measures are dense in the space of positive or the space of probability measure. It's very easy to show this. Now, in higher dimension, we have the same diagram. So consider this cycle and assume that, so Vi now is a subvarieties of codimension P. So it's no more a points, but it's a subvarieties. And we assume that the degree, the sum of lambda I times the degree of Vi is equal to 1, means that the degree of this cycle is equal to 1. Okay? So then in the same way, you can associate to this cycle, this combination, so sum of lambda I and the integral on Vi. So this gives us a map from the space of cycles of degree 1 to the space of positive closed PP currents that I didn't define it, but you can now imagine that it's just a way to compactify the first space. Okay? And again, now it's exactly like in the case of measure, you can see a current as an element of the dual space of this space. But now, instead of function, you have to use some test differential form. Okay, so the degree of this form is k minus p, k minus p. Also, you have some smooth positive closed PP forms, and this gives you examples of positive closed PP currents. But now, these smooth positive closed current are no more dense in the space of positive closed current. And this is a problem for the computation with positive closed current. Okay, so now I just quickly discuss the theory of intersection. So consider this example of two subvarieties. Then the intersection of assume that the intersection of V and V prime has a good dimension. I mean the generic case, the codimension is equal to P plus P prime. And then we can define the intersection with multiplicities. It's is well defined. Then in the sense of currents, we can define the intersection of the currents given by V and the currents given by V prime by the current given by the intersection, but we have to count the multiplicities. Yeah. So you can define the intersection in this way. However, it's possible that the intersection has the dimension larger than the expected dimension. So in this case, we say that we have a dimension excess phenomenon. Okay. So we can define this intersection if we don't have this problem. For the smooth case, we can always define the intersection of T and T prime because we have smooth differential form here, and then we just take the West product. So no problem for smooth case, but we might have problem for singular case. Okay, so the main problem in the theory is to establish a calculus with positive closed currents, in particular the regularization and intersection, and also to study the dimension excess phenomenon. Okay, So let me discuss the first problem. So now, here is the main theorem. So assume that we have a positive closed current of by degree pp. So we know that we cannot regularize this current. However, we can write T as the difference of T plus and T minus such that T plus and T minus are approximable by smooth positive closed current. And we can control the mass of T plus and T minus. Okay, so roughly speaking, we can regularize positive closed current. Oh, sorry. If we accept a loss of positivities. Okay, there are many applications of this theorem because it's very useful to compute with currents now. So I give you the first application in complex dynamics. So assume that F is now a monomorphic map. So Fn induce an action on the cohomology group. This is a hot cohomology group. This is just a linear map. Then you consider the norm of this operator, power 1 over n. Then the limit exists. Then the limit exists and is a finite number, and this is a dynamical degree. And this is a good invariant for the system. In particular, it's a bimeromorphic invariant. So if you modify the system using some bimeromorphic map, then you have the same dynamical degree. Okay, so let me give you some. So this is very important invariant of the dynamical system because it gives you some global information. So here, for example, you will take a generic subvariety of dimension q, and you take the image by Fn, then the volume of these varieties is similar to exponential of n dq. Q is the dimension of V, for example. So there is some mixed Hausriemann theorem in geometry, algebraic geometry, which implies that the dynamical degree first is a sequence of dynamical degree, first increasing, and then might be stable, and then decreasing. And then you can see that using this property, you can see that the system has roughly n expanding direction, because if you increase the dimension of V, then this number increases. If Q is smaller than R, then this number increases. That means that the new direction is roughly expanding. So we have roughly R expanding direction, S minus R neutron direction, and K minus S contracting directions. Okay, there are many work related to this property, in particular in lower dimension or when you have invariant vibration and so on. Okay, so I don't have time to discuss the proof, but the main problem is that the map f to n plus m is equal to fn composed with fm, but the action on cohomology doesn't satisfy the same property. Otherwise, it's a very easy exercise of linear algebra. And then what we have to do here, instead of working with cohomology, we work with positive closed current. And then we have to control the mass, and we compute with positive closed current and using the regularization theorem. This is the main idea in the proof. Okay, another application is the Grommet Inequalities. So for every map, we have that the topological entropy of F is smaller or equal to the algebraic entropy. So the algebraic entropy is given by this formula is essentially the logarithm of the maximal dynamical degree, and this is a finite number. So we have to remember that f might not be continuous, so it's not clear that the entropy is finite, but okay, we can prove this. So if f is holomorphic, if we assume that there is no singularities, then Dinh shows that we have the opposite inequality, and then we have equality. And we also have equality in many situations where f is not holomorphic. Okay? So the definition of entropy is quite complicated. It's not easy to compute the entropy, but in the holomorphic case, we can sometimes compute it precisely. So I skip this slide. And the proof uses somewhere some computation with singular positive closed current like that. So some integrand with singular forms. And then you have to use the regularization theorem. Okay? So now, I will discuss the next problem. So the main point here is that working with functions is simpler than working directly with currents. So this is the reason that the case of bidegree 1-1 is much easier than the general case. So roughly, we have the following things. So we consider the operator DDC, which is roughly the Laplacian operator. If T is a positive closed current of bidegree 1-1, then we can write locally DDCU, so T equal to DDCU, so it's a Laplacian of some function. So globally, we can have a problem with the cohomology. But if you choose a smooth form alpha in the same cohomology class with T, then T minus alpha has zero cohomology, and then we can write it as DDC of a function, a Laplacian of some function, and this function is essentially unique. So it's a canonical function associated to T. So it's very useful because instead of working with T, we work with a function. We can consider the value at a point and so on. Okay, so the point is that we don't have, it's not clear to have the same in higher bidegree. So now finally we have the, we solve this problem in the following way. So we consider this space Ck minus P plus 1. This is the set of all positive closed current of bidegree K minus P plus 1, K minus P plus 1, and of mass 1. So this is a convex compact set of infinite dimension. So we can think about a complex manifold with singularities, which is weakly compact, convex, and so on. And then we can define a function, a canonical function, ut associated to T on this space. So the formula is a little bit complicated, so I will not introduce here, but it's a canonical function. And it satisfies some property like this one. So we can see that, so this look like a complex manifold, and this, the function ut is look like a quasi-Pluri subharmonic function. So essentially like a subharmonic function. And for p equal to 1, we have a correspondence between a superpotential and potential. Okay? So then now we have a canonical function, and we can use this. However, the space now is of infinite dimension, and this is the main difficulty in the theory, because we don't have something like a Lebesgue measure. It's difficult to, we cannot consider the integrand of the function and so on. This is a very important difficulty. However, we can, we found a solution to avoid this problem. I don't have time to explain the details, but roughly we can work in infinite dimension in some way, which is more or less equivalent to the case of finite dimension, but have to change the point of view, and so on. We have estimate and so on. Okay, so let me skip this slide and give you some application. Now, this is a unique ergodicity. For simplicity, I assume that F is a holomorphic map, generic holomorphic map from the projective space Pk to Pk of algebraic degree D larger than 1. Now, you take any positive closed current of any by degree and of mass 1. You pull back it by Fn, and you normalize this. So we have a sequence of positive closed current of mass 1. And this sequence always converges to the same limit and exponentially fast. So you can see in this picture a consequence. So if you fix a nice open set, yellow, you like that. If you fix two varieties of the same dimension and same degree, and you pull back it by Fn with n large enough, then here you have some yellow, some red subvarieties and some blue subvarieties. Then the volume of the blue variety is almost equal to the volume of the red one. So this for every nice enough open set. And the proof uses superpotential. So how to prove this convergence? We just have to show that the superpotential of these currents converges to the superpotential of these currents. And you can show that the convergence is exponentially fast, and then you have this theorem. Okay, so now, this is another application. So this is a problem by Demailly, who asked the question to define the intersection of positive closed current of arbitrary bidegree. So the case of bidegree 1,1 is well known by the work by Chen, Levin, Nirenberg, Bedford Taylor, Demailly, and Fornay-Sibony. So now using superpotential, you can extend the theory to all bidegree. So instead of using potentials, we will use the superpotential. But roughly, under some integrability condition, we can define the intersection. We have some precise formula and so on. Okay, so this is a solution to the problem, the question of Demailly. Okay, see here another application. So very quickly, we consider the complex Monge-Ampere equation. So mu equal to ddc u to k with a given positive measure mu. So we want to solve this equation with u a Honda Pluripotential function. So the theorem says that this equation has a Honda continuous solution if and only if mu has a Honda superpotential. And this is a linear property. This equation is not linear, but however, the property to have a Honda Monge-Ampere potential is a linear property. Okay, this is another application of the superpotential. Okay, so now let me discuss the last topic. So, as before, take this example. You have two submanifolds or subvarieties of codimension P and Q in X. Assume that the dimension of the intersection, okay, we always have that the codimension of the intersection is smaller or equal to the codimension of V plus codimension of W. But it's possible that the inequality here is strict. And in this case, we have the phenomenon of dimension excess. So the intersection has dimension larger than the expected dimension. So now, the classical theory of intersection cannot apply the classical intersection theory in this setting. So the aim of the theory of densities is to develop a new theory of intersection which allow us to measure the dimension excess. So in particular, if you take two positive closed current T and S, and we want to know that what is the dimension of the intersection. So T and S might be very singular. The support can be equal to X. But however, we want to know the intersection in the sense of currents. What is the dimension of the intersection? And how large is the dimension? So the idea is very simple. We consider the product of these two currents. So these two currents, so this is the Cartesian product in X squared. And then we take somehow we want to understand the intersection of this product with the diagonal. So this is exactly the intersection of T and S, in some sense. Now, to understand this intersection, we try to dilate the coordinates in the normal direction to delta. We dilate the coordinate. And then, using this dilation, we can see the intersection better. And the intersection doesn't change if you do this operation. And then you can consider the limit of what you can see here. You can take the limit when the factor of dilation goes to infinity. So this is the idea, which is very simple. However, technically it's very complicated. First, we don't know how to dilate the coordinate in the normal direction. We can do that in this space. So E is the normal bundle of 2 delta in X squared. Here we can dilate the coordinates. We have coordinates and you can dilate it. But here you don't have a structure. So now we choose a good map, tau, from X squared to E, sending delta to delta, here's identity on delta. And then we will send the product of T and S from here to here. And then we dilate the coordinate and we look at the limit. So there are many problems because we have many choice of tau. Okay, and moreover, we don't have holomorphic map satisfy this property. So we have to choose a real map. But okay, many choice for tau, real map tau, good enough. Then here is the main theorem. So roughly, what we obtain is independent of the choice of tau. The family of currents we have is relatively compact. Then you can take a limit. The limit is not unique. We know this. However, they have the same cohomology class. Okay, so any limit that you take here give you the same cohomology class, and using this cohomology class, you can decide what is the dimension of the intersection of T and S, how large is the intersection. And we can develop the theory, you have some semi-continuities, and so on. Okay, so now here is an application of the theory. So take any map or correspondence from X to X, and let Pn be the set of isolated periodic points of period n. So the set of periodic points of period n is given by some equation. And the solution of the equation can be a variety of positive dimension. So we only consider isolated periodic points. We forget the family of positive dimension of periodic points, only isolated points. And we count the number of isolated periodic points. And you can show that the cardinality of Pn grows at most exponentially fast. And we can bound it using the algebraic entropy. So this is not obvious because in the real case, for the real dynamical system, we know that by the work by Kaloshin in particular, you know that many real dynamical system doesn't satisfy this property. So you can have periodic point growth as fast as you want. It's very surprising, but it's true. We don't have anything like that in the case of complex dynamical system, even if you accept singularities or you consider correspondence. And in many cases, for example, for Henon maps in any dimension, we can show that Pn is equidistributed. When n goes to infinity, Pn is equidistributed with respect to some property measure. So this is one example for Henon map in any dimension. But there are many families of maps satisfying this property. Okay, in this picture, you see the main idea of the proof. So gamma n is the graph of Fn, and Pn is a part of the intersection of gamma n with delta, because we are looking for periodic points. So it's like that. So you might have some variety of positive dimension, but we don't consider these varieties here. Then we will study this object using the theory of densities. So you consider the currents given by gamma n and another current given by delta, and you develop the theory. We have to study also a more sophisticated situation in order to prove that somehow gamma n, so there is some kind of transversality, of the intersection of gamma n with delta. So somehow we have to quantify the transversality and show that some estimate for the transversality is quite difficult. But we use the theory of density for current to study this problem and prove the equidistribution property. So very quickly, I want to mention that we can apply the theory to study the foliation also. So we have a unique ergodicity for foliations. So here is a simplified statement. So we consider a generic foliation by Riemann surface in P2. Then there are two possibilities. Either you have a unique directed harmonic currents of mass 1 and no algebraic leaf, or all directed harmonic currents are closed and supported by algebraic leaf. So you might have some algebraic curve as leaf of this foliation, and then in this case, you don't have any invariant harmonic measure or currents except these varieties. Otherwise, you have a unique harmonic currents. And you have some equidistribution theorem also as a consequence that is a little bit long to stay here. And finally, we can also extend, we can apply the theory to the classical intersection of currents. So under some condition, we can define the weak intersection of T and S. So this also answer the question of Jean-Pierre de Mailly for current of higher by degrees. Okay, so I think I stop here. Thank you for your attention.
Okay, thank you very much. Any questions or comments? Yes?
In the theorem about the growth of periodic points and
Yeah.
algebraic entropy, do you know when equality holds or if it ever fails in some examples?
Or when you have the equidistribution, then you have, of course, you have the equality up to some order. Yeah, I mean, little o of something. Yeah. So, but
Are there
not in the
explicit
general
examples
case.
where equality fails, where you don't have equidistribution then?
I don't know. Maybe in dimension 2, there are some result by Favre, Jacques Favre, who count the number of periodic points.
Okay.
Only in dimension, in very particular situation of birational map and so on. But in general, I think the strategy is not to, okay, we have a good upper bound, and the strategy is to prove directly the equidistribution. Then you have everything.
Then you get
This is a strategy, general strategy. So it's not a priority to look at the,
Curious.
yeah, in my point of view. Yeah.
So any other question or comment? Hold on. You use them.
When you prove equidistribution, do you have an idea of the rate of convergence to this?
I think it's a very, very difficult problem. So let's say for most of the steps in the proof, we can have, quantified rate of conversion, except maybe one step. And more than that, I think we need some really new idea for this problem. It's a very good question. For the moment, I have absolutely no idea how to do that.
So anything else? Okay, if not, let's thank the speaker again.
Thank you.